Okay, let's continue on with the exceptions of the Aufbau principle. Remember how I told you guys in the last video that exceptions to Aufbau, you're going to see them in group 6B and in group 1B. Group 6B is the one that starts off with chromium and everything underneath it. And group 1B is the group that starts off with copper. So let's go ahead and do the electron configuration of copper using Aufbau. And then we'll talk about why we need to do an exception to Aufbau to give it the really good electron configuration, the accurate one, the one that is more stable, okay? So looking at copper, we can go ahead and put argon as our noble gas. Okay, and that accounts for the first 18 electrons, just like we did with chromium. And then we would write 4s2 and then 3d9. Because zinc would be 3d10, copper is 3d9. So this is copper. Okay, so this is wrong. Why is it wrong? Because if we look at the orbital diagram, this is the 4s. And then this is 1, 2, 3, 4, 5. This is the 3D. Single, 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 single. Oops. Sorry about that, guys. Here we go. Single. And then 1, 2, 3, 4. There we've got our 9. Okay, remember what I told you guys. It is most stable when it's completely filled or half filled. And you are allowed to promote one electron from the S to the D. Can you see that if you promote this one electron, bring it over here, it makes this completely filled, and then this is half filled, and it's super duper happy and very, very stable. So we're going to take this one electron, bring it over here. So your 4s is half filled, and then your 3d is now, because of this promotion of the electron, is completely filled. So the electron configuration of copper is not 4s2, 3d9. It is 4s1, 3d10. Okay, that's the case. These exceptions for Aufbau, for the Aufbau building up principle, are, like I said, again, to repeat it for the gazillionth time, group 6B and group 1B. Now, how does this differ from the excited state? These are all ground state. This is a ground state. I know it looks like it's excited, but it isn't. It is, you promoted it. It is not an excited state. This is the ground state. This is the most stable state. If you have an excited state, for example, let's say we've got phosphorus. Phosphorus would be neon, 3s2, 3p3. That's what phosphorus is. That's the ground state of phosphorus. No exceptions to Aufbau. What if an electron got excited and it's neon 3s2, 3p2, 4s1. This is not a stable state. This is not the ground state. It's still all the correct electrons of phosphorus, but you can tell that one of these electrons got excited, pushed up into a higher level for us. So you would recognize this as an excited state, and this as a correct ground state. Okay, be able to differentiate between the two. All right, good. Let's see. What else do we need to do here? Let's talk now about magnetic properties. There are two terms I need to tell you guys: diamagnetic and paramagnetic. Okay. So once you do the orbital diagram of whatever element, if you find that you have unpaired electrons, then that substance is paramagnetic, meaning that it can be weakly attracted to a magnetic field. So let's put that down. So paramagnetic, a paramagnetic substance is weakly attracted to or by a magnetic field due to unpaired electrons. So anytime you have unpaired electrons, it's usually going to be a paramagnetic substance. The other term you need to know is diamagnetic. A diamagnetic substance is not attracted by a magnetic field because it only has paired electrons. Remember how we mentioned earlier in in the last video, I think, all of group 2A completely paired. Everything is over here is going to be all paired electrons, so that would be considered diamagnetic. All the noble gases, diamagnetic. All these guys, zinc and this bunch over here in group 2B, diamagnetic. All the others that have unpaired electrons, paramagnetic. Okay? So you got that term down, hopefully. All right. Now we're ready to talk about periodic properties, and we'll be able to wrap up the key parts of this chapter. Atomic radius. All right. As you go down a group, the atomic radius increases. Bigger, bigger, bigger radius. So if you compare lithium to sodium to potassium to rubidium to cesium, cesium is the biggest. Okay, big radius. Lithium's the smallest. So as you go down a group, atomic radius increases. What happens as we go across a period? As you go across a period, atomic radius decreases. So if you're going to compare the radius of fluorine to lithium, fluorine, even though it's got more electrons, more protons, more everything, is going to be smaller. Fluorine is over here. Think of lithium as over here. As you go across a period, the atomic radius goes down. Now, why is that the case? It has something to do with the increased nuclear charge, meaning as you go across a period, you're going to have more protons. And when you have more protons, but the same shell, those protons are going to pull at those electrons more. So the electrons are going to be more attracted to that nucleus because the protons are pulling at those electrons. And as the protons pull at those electrons, pull them in, then the radius gets smaller. Okay? While over here on this side of the periodic table, lithium, let's take a look, for example. Lithium's only got 3 protons. Okay? And fluorine's got 9 protons. They're in the same shell. They're both in the second shell. The electrons of lithium, they've got 2 electrons in the 1s, and then it's got 1 electron in the 2s. All right. So these 2 electrons are sort of like buffering this 1 electron from the proton. So basically it's shielding this 1 electron from these 3 protons. So there's enough space. But here we have 9 protons. They're pulling. There's a 1s, but then your electrons in the second shell, whether it's the 2s or the 2p, this is not able to cancel the effect of these 9 positives. These 9 positives pull at these outermost electrons and bring them in. So this is called effective nuclear charge. The more the protons in the same, this is within the same shell, all right? We're not talking as you go to a new shell, because every time you go to a new shell, the electrons are even further away from the nucleus. But we're talking within the same shell. The more the protons, the more they're going to be able to pull at those outermost electrons, all right? And that's why as you go across the period, you have a smaller radius. As you go down a group, you get a bigger radius, okay? So if I were to ask you, who's got a bigger radius? Let's say I put this, let's say I have, let me try to do something that doesn't look overly obvious, but let's say I have sulfur, oxygen, and let's say I have selenium, and let's say I have arsenic. Okay, and I tell you which one of these is the biggest radius. Okay, well, we can see that oxygen, sulfur, and selenium are in the same group, right? And selenium is going to be bigger than sulfur, which is going to be bigger than oxygen, right? So selenium is bigger than sulfur, which is bigger than oxygen. Well, what about arsenic? Well, arsenic and selenium are in the same period. And remember how we said as you go across the period, it gets smaller? So that means selenium is smaller than arsenic. So that means arsenic is going to be the biggest, and then selenium, and then sulfur, and then oxygen. So for a test, for an exam, you should be able to rank things. I'm going to make them pretty straightforward. You should be able to compare them pretty easily, either down a group or across a period. And if I'm going to mix and match down a group across a period, it's going to be something as straightforward as this. Okay, so just a few more topics left. We're going to talk ionization energy, electron affinity, and then their trends. And then I'll mention really quickly some periodic properties in the different groups. I think that's what we have, periodicity and main group elements. Okay, good. We're all set for this one.